So, hey Philip, welcome to episode 5 of Cozy Conversations. So, why don't you introduce yourself, give us a bit about your background and how you ended up in AI safety?
Sure. Thanks for having me. So my full name is Philip Quirke. Most people call me PQ, so feel free, but I'll answer to Philip or Phil or anything. I've been in IT my entire life. My most recent commercial role was running a team of 30 people, delivering cloud services to the New Zealand government. But I've been in a number of startups as a developer, architect, business analyst, project manager, team lead, that sort of thing. So I consider myself somebody who builds things and innovates. I've always done that my entire life. So about a year and a half ago now, obviously I started getting interested in AI and could just see how quickly it was moving forward. And I always gravitate towards roles and opportunities where they have more than just a pay packet, a positive influence on society and culture. And AI safety seemed very much aligned to that. And also was I have quite a strong commercial background, so it was quite clear to me that there was a lot of emphasis going to go on AI capability and then rolling it out as fast as possible, and a lot of commercial push to do that. And so um, AI safety was even at that stage obviously underserved and was going to continue to be. By the way, I tend to talk quickly and I just keep talking. So if you have a question, just jump and talk over the top of me and ask it, because otherwise I won't stop. So I started reading up on safety, and then about August last year, I decided I should get serious, and I left my role and started studying full time. And I guess, and so one of the first groups I joined was this AI safety forum, and I think it was via this route I came across an apart research hackathon weekend, which I went to, and they had 200 open questions from Neil Nanda on AI safety, basic questions which people didn't know the answer to, which was a real indication of just how young the field is and how open it is and how many opportunities there are to add value. So I found that weekend quite hard. I didn't have the skills, I didn't have the background. It's not necessarily a field that you can get into. It's not as well structured as, say, a university course that's been run 10 years in a row. But anyway, I wrote a paper at the end of the weekend, which was basically just an idea. I couldn't prove anything. And the topic was, how does a transformer model do addition? 1, 2, 3, 4, 5 plus 6, 7, 8, 9, 0. How does it do that? And the fact that nobody knew that was just mind-blowing to me. It's just such a basic fact. And people knew it did it, and they could tell you where in the model the addition was happening, but they couldn't tell you how the calculation was happening. So after the weekend of part research, also known as part lab sometimes, said, look, come and work with us some more on us. We'll mentor you towards writing a paper on it. And so they did. And they're a great organization, which I'd recommend if you kind of want to get more of a technical side and push forward. And I was good on the research side and on the thinking side, but the writing of a paper, I've never done that in my life. So they mentored me very well on that. So through that process, I learned a lot about transformers. I guess there's many ways to learn about AI safety, but my path was trying to learn a lot about a small area. And through that process, you learn things about transformers, which are probably a bit too detailed for this point. So anyway, finished my first paper and submitted it to one of the conferences, and it got accepted. I think it just squeaked in. I had 4 reviewers, and my scores were poor, good, and excellent. And so using that feedback, we improved the paper, and it got accepted. But I think it just sneaked in. And then since then, I've been working on a second paper, which is an extension of the first, to go into more depth about how addition works, see if we can use that to work out how subtraction works, see if we can not only work out how these models work, but come up with a really high standard of accuracy. All the transformer models, if you ask them to do a task, they will do it, and in general they'll do it really well. But if you went to one of the transformer model providers and said, I'm going to bet my business on using your tool, are you certain it's always going to answer questions in this task area correctly? I can't imagine they would give you a guarantee, and that's quite worrisome. And so the second paper, which is up on arXiv, is about saying, what if we wanted to be really, really, really sure, certain that this task was actually being done accurately all the time? And so we've provided one example where 5-digit addition, where we show that it is provably accurate, and through that effort come up with a process on how you can, for a task, kind of prove that it's 100% accurate. And our continuing goal is to kind of expand that. At the moment, that process is very manual and very human, and requires some a big insight somewhere along the way, and that won't scale. So we want to leverage our first insights and our process to get the next insight and the next task provably correct, and see if we can scale it up. So that second paper went up in arXiv and has been submitted to a conference just in the last couple of weeks. So that was great. And then one more minute and then my intro is finished. Leveraging my kind of background in kind of large organizations. No, sorry, go back a step. So Long-Term Future Fund have just recently funded me for a career pivot.
Congratulations.
So that's fantastic. Yeah. So I've been self-funded for the last 5 months, I guess, with a very supportive wife, which is lovely, but great to have a bit of runway ahead. And because I'm secure on that, I've just recently gone off to OpenAI and said, hey, I've got this paper, I've got this large body of work which we could be working on. Give me funding to bring another 3-4 people into the effort for a year to work on it, because we're making progress on AI safety, but the people in our capability are making progress at a massive rate of knots. And so the more people we can get working hard on AI safety, the better. And to your point, Chris, about there not being many AI safety jobs in this part of the world, Apart Research is a kind of a remote first organization. And like my mentor is in the UK, which means...
That was Faisal.
Say again?
Who was mentoring you? Was that
Faisal? Yeah, Faisal. Yeah.
Oh yeah. I met him when I was.
He's a great guy. Yeah. He seems to be like, he must have 40 papers to his name where he's been mentoring people like me, or some of them he's lead author on, but he just seems to be everywhere. Just unbelievable workload, that guy. So yeah, meeting with him morning and evening, but apart from the odd hours, they're an organization I'd recommend if you're hitting the technical route to try and get in there. And that brings us to today. So I kind of think of myself as an AI safety researcher. I'm funded for a period of time, trying to get more people into the field. I have a flow forward set of work that I'm working on. Cards on the table. There's nothing, I can't say hand on heart that the path that I'm researching will pan out into a major finding. We might hit a brick wall. We might find that it's not as useful as I hope, but it's different enough from what other people are doing that if I was a philanthropist, I'd want to see it funded, because I think we should be looking down as many different paths at the same time as we can. So how's that for an intro?
Oh, yeah, that's a great intro. Oh, by the way, so yeah, congrats on the LTFF grant. Can I add that to the achievements thread?
Sure, please.
Okay, cool. All right, I add it to the achievement threads afterwards. I just find that if I write it down when people achieve stuff, I'm hoping that people are gonna see, oh, this person got a grant, maybe I should consider applying to this fund as well.
Yeah, I think so. I mean, it's kind of like looking for a job. It's a little bit of a numbers game. Just apply for everything. Um, if you're not in, you've got no chance of winning. So, yeah.
That makes sense. What was the process like of like applying to the LTFF? Did you find that very onerous, or was it not too
No,
tough?
it's it's a 2-page written submission, and that was it really. And then it was just wait. They're not very fast. Yeah, the
How
standard
long did it
lead
take?
time is 8 weeks. In my case, it took longer, and I'm not sure if that's because I made a administrative mistake in my form or they made a mistake. But anyway, 8 weeks is their standard time. So
Oh, okay. Cool, cool. So mentioned you were being mentored by Apart Research. Maybe you could tell us a bit more about that mentorship.
yeah. So it came out of the hackathon. They invited me to continue working there. They're a small organization. They've got, I think, like 3 or 4 kind of core paid staff, and they've got probably 40 people like me, people trying to enter the field. Um, lots of smart people, lots of motivated people, and they you're obviously you expect to do the bulk of your work yourself, but if you get stuck, then you have somebody to talk to, right? You have somebody to ask questions of. You can waste a lot of time if you get stuck, and it's really good to have objective people to look at what you're doing, because it's a new area for all of us, and our knowledge is limited, and having objective people, particularly Faisal, who calls himself Kiko, is often his kind of nickname. Having people like Kiko looking at it is really, really useful, um, just for a bit of objectivity. So yeah. So they are happy to support you on whatever you want to do. I think in the conference that I got my paper into, I think they got 2 or 3 papers into. The conference that I've submitted my second paper to, I think they've submitted 2 or 3. And each of those will have a lead author by a person who's trying to get into AI safety, who's put on a lump of time to do a lump of work, and then the help from Apart Research to get their papers up to the standard that are required for, an academic conference. Which, for clarity, for me, the abstract, the introduction, and the conclusion were really new learning things for me. Like the meat, the bulk of the paper, the meat of it, I could do just by applying my IT knowledge and my smarts to the problem itself and come up with some conclusions. But the abstract, the introduction, and the conclusion, they have different purposes. They're to take somebody who knows nothing about the topic, and within a paragraph introduce them to the topic, and then within another paragraph tell them what this work does, and another paragraph tell them why it's important to the overall our safety. So there's some sorry, and also related works about seeing what everyone else has done and how it relates in. So there's these kind of surrounding pieces you need to get it to be a academic paper that were brand new to me, and they were and the Apart Research were hugely valuable to me in helping me through that process.
What made those components like very challenging? Is it that you have to try and communicate a lot in quite a concise amount of space, or is it something else?
Yeah, it's that. If I'd written them myself, my abstract would have been about my work, and my introduction would have been about my work, and my conclusion would have been about my work, right? But
Oh,
they're not. The abstract is kind of like a sales pitch. You've got somebody who's reading. They say you assume that the reader is only going to read the abstract, and then look at all the pictures and the explanations under them, and then read the conclusion.
mm,
So that alone has to carry the message um, of your whole paper, just the abstract, the pictures, and the conclusion. And the abstract's got to be, it's a bit of an advertisement. It's got to be attractive enough that you say why the person who's only reading the abstract should go further into the paper. Yeah, so and it's got to be very concise. The abstract is often 6 sentences. So, what the field is about. So you've got to spend a paragraph talking about what is mechanistic interpretability, because you can't assume that the person coming in even knows what that is. And you've got to, in that same paragraph, say why AI safety is important, because you can't
Wow,
assume
that's a lot.
they know that, because it might be a physicist, or it might be it could be anybody. And then you've got to say what you're doing in like a paragraph, and then you've got to say how what you're doing fits into the overall field in kind of a paragraph. So it's very, very concise.
Well, cool. I think we should probably get into a bit more detail on those two papers. Uh, so maybe just at a high level, could you tell us a bit more about the addition in Transformer papers? And then if people are interested in the details, then when we open up the floor to questions, that's when they can find out a bit more of the details.
Sure. So addition, if you just kind of think about when you learned addition, the first question you were given was probably 1, 2, 3, 4, 5 plus 2, 2, 2, 2, 2. And that's kind of a simple question, because there's no carry ones. There's no pair of digits that you have to add together where a 5 and a 7 gives a 12. So you write down 2, but you got to carry 1. And if you think about how you do it manually, you start with the last digit, like the ones, and then you do the tens, and then you do the hundreds, and then you do the thousands. But a transformer model, if you kind of think of the transformer model doing English, it's like Bill and Jane went to the dairy. Bill bought a bottle of milk for, and then the transformer model has to give the next word. So if you kind of write down an addition problem, 1, 2, 3, 4, 5 plus 2, 2, 2, 2, 2 equals, the transformer model's got to work out the highest digit first, and then the second highest digit, and then after a few digits, then give the units digit. So for a start, it's working backwards from the way that a human would do it. So that puts it at a disadvantage. And then there's a range, like we talked about the very simple addition problem. A very hard addition problem is 4, 4, 4, 4 plus 5, 5, 5, 6. And the reason that's hard is because the units give a carry 1, and then the tens also give a carry 1, but you don't know that until you've worked out the units value, because the 4 and the 5 and the tens, sums to 9. So that's not a carry. But because there was a 1 carry from the units, then it generates a 1. So you end up with this cascading 1. And, in 4, 4, 4, 4 plus 5, 5, 5, 6, the 1 cascades all the way up to give you the answer 10,000, right? So when the transformer has to name the first digit 1, it's really got to have done all that carry calculation all the way back to the units before it can work out whether the first digit is a 1 or a 0. So it's the transformer model's at a disadvantage because of the ordering of the question. So this is one of my first learnings about transformers. I spent ages trying to work out how the model could possibly be doing that. And I couldn't work it out. It was just like, this is impossible. And then I thought, well, I should just put in these really hard examples. And to my surprise, my first model failed on those hard questions. So it could handle a carry 1, and it could handle a 2-step carry 1. But if the carry 1 cascaded up 3 or 4 or 5 digits, it couldn't handle that. And the insight was that what I thought was a perfectly accurate mechanism wasn't. It was accurate for 99% of questions, but for the 1% of hard questions where the 1 cascaded 3 or 4 or 5 digits, it couldn't handle it. And it was only after I realized that I could start to work out how the model was doing it, because it didn't need to know. It didn't need to know how to do it perfectly. Well, it wasn't doing it perfectly, and that kind of gave me a hierarchy of complexity of questions, from the first ones you give a child to learn, 1, 1, 1, 1 plus 2, 2, 2, 2, up to the hardest one where the 1 cascades 5 digits. And then I found the model could solve the easy ones, but not the hard ones. And there was a cutoff point. And that gave me enough insight, plus some other diagrams that are shown in the the paper that I could work out how it was doing it. That I could come up with a hypothesis for how it was doing it. So again, a learning for me. I went to my Kiko, my mentor, and said, "Yep, I've solved it. Here it is." He said, "Prove it." And I said, "Look, it must be doing this. There's this is the only way it can be doing." And he said, "Prove it." And then another couple of weeks of learning Python and a technique called intervention ablation, where let's not go to the details, before I had enough proof that to his standard that I had proved it. And then that was kind of paper one. Any questions on paper one before I kind of give a bit of detail on paper two?
That makes sense.
Cool. So in paper two,
I have a question sort
sure.
of relating to the other literature.
Sure.
I remember reading a paper, I think it was by Neil Nanda, about modular addition, and I'm wondering how similar like your paper was to that, and like whether either one built off the other, and how similar the tasks are.
Yeah. So obviously Neil Nanda came first, and he's a fantastic guy, and he's got wonderful papers, and that was a wonderful paper. No, it's completely different. I know modular addition and addition sound very similar, but with addition, you start off with two 5-digit numbers, and you end up with a 6-digit number. So for 5-digit addition, there are 10 billion possible combinations, giving 10,000 possible answers. With modular addition, if you have like a 2-digit answer, you end up with a 2-digit answer. So it's actually a simplification problem, whereas addition is kind of an increasing complexity problem. The other thing that's stunning about Neil Nanda's addition paper is that the model learnt a type of Fourier transform. I'm not sure how many of you know about Fourier transforms. It's reasonably tricky, and when I went to university, it was kind of like a stage 3, level 3, year 3 type paper. It's not trivial stuff, but the model learnt it, and that was the technique that the model implemented to work out modular addition, and the model picked 3 like not 1, 2, and 4, but 13, 19, and 31 or something, 3 different prime frequencies, which it then used to implement modular addition. So very complicated technique that the model came up with. And when I read that, I was a bit dismayed, because there was so much math required to work out the solution. It's like, far out. If all models are like that, that's going to be really hard. But luckily, that's not so. So my model does nothing like Fourier transform. It's much more mechanical. It's much more. It feels more like a program. It breaks the overall task down into subtasks, and those subtasks answer the question perfectly a percentage of the time. So it learns the first subtask, which is like that most simple form of addition, and then it learns how to do a make carry on 1 digit, and that gives it another 25% of the answers correctly, and then it learns 2 digits. And in my first paper, that's where it stopped. So for whatever reason, and the model's the same, if you change the number of heads or the number of layers or the number of digits, it always comes up with the same algorithm. So there, as far as I know, there's only one algorithm the transformer finds for addition, and it feels much more like a computer program than a mathematical proof. Yeah, but I certainly read that paper, and it certainly seemed like the bar was very, very high, but my model, my paper showed that the bar for understanding is quite a lot lower and simpler in my case.
That quite surprised me, because I had seen the Neil Nanda paper, and then that used Fourier transform. Like, oh my god, if you're going to do addition, how complex is this thing going to be? So yeah, I had okay. So about the first paper, one question was, so suppose you have a carry for the first digit, then it makes it another digit, and does that cause issues for your approach?
As I understand your question, if with the paper one, it could handle a carry that cascaded 2 places, but not 3 or 4 or 5.
Yeah.
So that was its cutoff point, and it was kind of, that was I guess, the model is trying to provide the optimal mechanism that it can, but it's also constrained by how many attention heads I gave it and how many layers I gave it. So
This is a one-layer transformer, right?
yeah, it was 3 attention heads, 1 layer. Yep. So
Cool.
it appears that that's the best it can do with that much freedom. So in paper 2, we used a larger model to give it more freedom, and it did better.
So just to clarify, like, let's suppose you have like the number like 11 and 99, then you end up with like a 3-digit thing. And then the question I was asking about is like that would cause a cascading issue if you kind of put down, because then all the digits would be offset by one more place because you've added in that extra digit.
All right. So the format of the question and answer was always, if you added 1 1 plus 2 2, the answer is 0 3 3.
Oh, okay.
So for 5-digit addition, the answer is always 6 digits. That's how we frame the question.
Okay, that makes sense.
Yeah, yeah.
Cool.
Yeah.
All right. And one other question I had about the paper was, have you considered doing any causal interventions? Because it looked like you were using mean ablation, where if people don't know that, I believe it's just that you take the mean activation over some data set and you just kind of replace the activations by that kind of mean. And that seems to measure, like whether it's involved in like some kind of way, but it doesn't really establish that you can directly control it with that component.
Yeah, yeah. That technique's got about 3 or 4 names. So another name for it is intervention ablation. Exactly the same technique. And yes, that's exactly what mentor Kiko said I had to do to prove it. So say you had the technique there is, you pump the question 2 plus 7 through the model, and it gives the answer 9. Sorry, let's say 2222 plus 7777 equals 99999. And so you watch all the values going through the model. And then you have a separate question, which might be 11111 plus 777. And you pump that through the model. And at a particular node, you record what the second question did with that node. And then you rerun the question you're interested in, the first question. But when it gets to that node, you overwrite that node with the value from the other question. And you expect a different answer. And it's not just you expect any old different answer, you expect a specific different answer based on the question that you put in. And because you've overridden one node, you expect just one digit of the answer to change in a very predictable way. So by doing that, you can prove not only that node's involved in calculating that answer digit, but it has this specific behavior. And then you can form very specific pairs of questions, which can demonstrate it's doing this calculation and not this calculation. So yes, I did a lot of that.
Oh, okay, cool. Just because like I might have missed it because like when I was trying to go for the paper to prepare, I just didn't see any of that kind of stuff.
Yeah, it's pretty buried in like appendix
Oh, okay.
8. And it's probably also, you really got to look at the collab to actually see it. Again, one of the things about writing a paper is you're only allowed 8 pages. And because you're trying to tell the story in pictures, a lot of the detail just can't fit in those first 8 pages, and you shove it into appendixes and just reference it.
Cool. So anyone have any, yeah, cool. Yeah, you've got a question. Yep.
Are you on mute?
Yeah, sorry, I was trying to unclick the mute button. Yeah, sorry if this question is like a little bit in the weeds, but I've heard that Mech people talk about this programming language called RASP, I think it's called, that is able to, yeah, you're nodding, so you know all about this.
No, a little bit.
Yeah. I was wondering, you said that this model learned sort of like programs, so instantly I sort of thought about, is this something you thought about, like trying to translate this addition program into RASP and then being able to study it that way? I don't know a lot about this topic, so it'd be interesting just to learn more about MECINTERP and RASP and how that all interconnects if that's something you're across.
Yeah, I'm trying to drag it out of my memory. My recollection of RASP, I might be completely wrong, is that it goes from the if I write a simple program, 4 or 5 line program in a particular code, and then it translates it to create the model. Whereas I'm looking at the model that evolved itself through training and trying to work out what's the program that it's implementing. And the reason that the two, the beauty of the large language models is not that humans have programmed them, it's that evolving them generates this amazing, strong behavior. So the goal is not to, RASP, as I recall it, is an interesting experiment. Sorry, it's not experiment, it's an interesting technology, but the programs that RASP produces are nothing like the models that get evolved naturally. And that's why people have so much trouble understanding the LLMs, because the implementations they evolve naturally are just bizarre. They don't feel like a human programmer wrote them. They're not aesthetically pleasing, they're not optimal, they're not consistent. Like I would expect every digit to be calculated in the same way, but actually some of the digits are calculated in slightly different ways from other digits, just because everything's done in parallel and the parallel nodes aren't talking to each other. So they decide how they're going to do it. So I guess why I'm working on the approach I am is that I want to understand, in the same way that Neil understood that modular addition was done with Fourier transforms, and my one is done with more understandable unit tasks. I'm hoping that if I do 5 or 6 models, I'll start seeing repeated unit tasks. And in fact, I'll be able to search a model that I don't understand the algorithm of for those unit tasks. And just like a crossword, that'll start filling in some of the letters in the crossword. I still won't, the technique won't tell me the algorithm that the model is implementing, but it will tell me some of the letters in the crossword, and that's a clue. That makes my task of interpreting it easier. Does that answer your question?
Yeah, so I guess you're saying that you don't think that it would be possible to translate the program that you saw back into this RASP language because it's just not very compatible with the way that humans write programs.
Oh, actually, like for paper, for paper 1 and for paper 2, I did actually translate it back into, into Python, and then I ran the Python. But for paper 2 in particular, if a human programmer came along with you and said, I've written a Python routine that does addition, here it is, you'd fire them because it's convoluted, it's not consistent per digit. There's a number of aesthetic, the model doesn't have the same aesthetics we have or value the same things in programming that we do. So it doesn't look, like a human wrote the program, because it didn't, right? It was evolved in the transformer model. So in a similar way, if we get a human to write an algorithm and we put it into a model, it will work. But it won't be the sort of model that we'll see in the large language models. And one of my end goals is to try and reuse the stuff that I'm doing in large language models. So I want to understand some of the techniques that the large language models evolve.
Yeah, I see. Yeah, thanks for that.
No worries.
Evan.
Yeah, so maybe you didn't mention this or maybe I didn't catch it. How did you tokenize the numbers?
Oh, right.
Did you just
Yeah,
give
sorry.
each digit a token?
Yeah, that's right. So I only have like 13 or 14 tokens, and the tokens are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, plus, minus, equals.
Yeah, okay.
So yeah, in effect, that's there's an interesting paper called GOAT, G-O-A-T, Good at Arithmetic, I think it is, and they show that large language models which tokenize the numbers 0 through 9 as 10 distinct tokens do a lot better than languages which tokenize 3 as sometimes as token 45, and sometimes they'll tokenize 3, 4 as token 182. You know, tokenizing the individual digits as individual token is a big step towards good performance of arithmetic and large language models. And for some of the large language models, they actually tokenize the digits differently in different languages, which means that the large language model has to learn arithmetic in each language.
Yeah, that's quite amazing.
Yeah.
Yeah, makes sense.
Cheers.
Cool. So why don't you give us a high-level understanding of your second paper, Increasing Trust in Language Models Through the Reuse of Verified Circuits.
Yeah, so there's kind of 2 or 3 or 4 main drives. The first is I was annoyed that my first model didn't do arithmetic perfectly, and so I wanted a model that would do addition perfectly. And then as I explored that, it was really, really, really hard to know what a level of proof of perfection was. So we came up with a heuristic that said if I can do 1 million questions and get 1 million of them right, and 1 million successive questions and get them all right, that's not proof, but it's it's evidence that it might be perfect. And then if you think of like 10-digit addition or 15-digit addition, let's say 10-digit addition, then the case where the 1 carries forward 9 positions, that's incredibly rare, right? It's much more rare than 1 in a million. So even if it does 1 million questions correctly, that it might not get an example where the carry 1 cascades through 9 positions. So it's only by understanding all the use cases, all the edge cases, and making sure that those edge cases turn up often in the training data, so that the model has a chance to learn techniques to deal with them, and then assuring that all those use cases are in your training data, in your test data, so that you can be sure that you've tested all the use cases. Only when you've done both of those can you be the next level of sure that your model is accurate. But even that's not enough, because what if there was a use case, a really edge use case that you hadn't thought of, just hadn't occurred to you, and so it wasn't in your training data and it wasn't in your test data, and you might say, I strongly believe this model is accurate, but in fact it's not. So then we come up with this definition. The third level of making sure it's correct is to say, right, well, I'm now going to look at how it implements the model, and I'm going to work back to actually, what are the chunks of calculation it's doing, and I'm going to map all of those calculations to a framework, and then I'm going to convince myself that that framework is actually addition, and it does addition correctly, and that's what we did with 5-digit addition. And so in paper 2, we had to make the model larger, so it was 2 layers and 4 heads, I think, or 3 heads, still 3 heads. And once you've got a model that can do 1 million questions, you understand how it works, you've mapped that understanding of how it works to, in this case, a mathematical framework, and everything lines up, then you can call the model known good. So that's a term that we defined in the paper. It's a known good model. So that's the kind of verified, accurate, trusted model bit. But then, there's a lot of effort that goes into getting to that level on your model, and that doesn't scale up. So what can you do? How can you reuse that known good model to do the next task? So we took on subtraction. Subtraction and addition have a lot of things in parallel, and what we found was that if we took a new model and we initialized it with the known good addition model, and then we trained it on 20% addition questions and 80% subtraction questions, then it was motivated to remember how to do addition by the 20% of addition questions. It learned to do subtraction because of the 80% subtraction questions. And we ended up with a model that could do 1 million addition and then 1 million subtraction questions without any error. And we showed that we call it a mixed model because it does both addition and subtraction. We showed that the mixed model reuses all the addition circuits that we'd inserted at the start and then added some additional circuits. And that's really as far as we got. We have not yet fully explained how the subtraction process is calculated, and we haven't mapped it back to a mathematical framework. So we can't say the mixed model is known good, but that's one of our next tasks. But so that's kind of like reusing our knowledge of addition to help us prove subtraction is known good. And then in terms of large language models, it would be nice if you could say with confidence that large language models do addition perfectly, or subtraction, or some other things, or logic, if they do logic perfectly, but you can't prove it. You can do 1 million tests, but that's not a guarantee. So then we really only got to the proof of concept that these large language models, you can find out what nodes they use to do addition. Like you can kind of trace the calculation and work out where it's doing addition. That's great. And also, there's another paper that says in these large language models, there's a number of neurons that are just never used. They're called dead neurons. So there's chunks of the model that are just not used. So our proposal is that we take our known good model that's perfectly accurate, and we're going to retrofit it into a large language model by replacing the nodes that it currently uses to do addition. And if we need some extra nodes, we'll use the dead neurons. And you'll end up with a large language model where you've basically taken a punctured tire off the car and you've put on a known good tire to replace it. And if we did that with with mathematics, and if we did it with logic, that would make those models more trustworthy, because we would be sure that just in these tight areas that the algorithm was perfect.
Nice. So one question I did have about that was, I noticed in the paper you said that attempts to freeze useful attention pairs or weights ended up decreasing the accuracy. So it sounds like you did some kind of further training, which, obviously would have modified the known good circuit. So wouldn't it be the case that the circuit is no longer known good after you've done that process?
Yeah, very good. So very well spotted. So I'll just expand on that a bit. So when we inserted the known good model into the mixed model that before we trained it, we had 2 or 3 different approaches to it. One was just right at the start of training to put in the known good model and then just let the model train itself. And as Chris rightly says, then you've got the strong risk or strong likelihood that the model's going to alter the behavior of those nodes. So you can't assume that it can still do addition accurately, and you can't assume that those nodes those weightings that we put in there are retained. So we had another approach, which was to say, stick in the known weights at the start of training, but then run the model 1,000 training cycles, and then put the weights back in again, just for the nodes that we know are part of addition, and then train it for another 1,000 cycles, and then put the same weights again. So just keep putting the weights back in. So by the end of training, you're guaranteed to still have the addition circuits unchanged in the model. That second approach didn't actually work that well. The model never got very good at subtraction. So another way to say that is, if we just put in the initial weights, the model got, by the measure of the 1 million questions, the model got very good at addition and subtraction. But yes, we now need to reprove that the model is using the addition nodes for the same purpose in the mixed model as it did in the addition model.
EJ.
But the advantage we have is we've already written a whole lot of test cases for the addition model, so we can just reapply those to the mixed model. Yeah.
Cool. EJ.
When you are putting those model weights in that you reset every 1,000 training steps, so that section that's being reset is only a subsection of all of the neurons, right?
Yeah.
I was
So
wondering
go ahead, sorry.
if instead of resetting them every 1,000, if you just don't update them ever, but and only let the gradient descent work on the remaining neurons, do you know what happens then?
Yeah, we thought of that, and very insightful. We could technically I didn't have enough time. We weren't smart enough to change the gradient descent program to not change just the neurons that we knew were useful, because those neurons are kind of like scattered across the model. So we haven't done that experiment because it was technically challenging. We ran out of time. My intuition is that we'd run into the same problem as the replacing every 1,000 cycles. The model would do addition very well, but would not get as good at subtraction. But good insight. Yeah.
Another question. So have you considered putting a penalty for diverging from the initial weights? I think I've seen other models use that kind of technique, like a penalty instead of like a strict replacement.
Yeah, so the short answer is no. The longer answer is I'll kind of come back to that in 1 minute. The model algorithm, all the different training ones we did with all the different heads and they all use the same algorithm, but they have this horrible habit, from my point of view, of changing where they do the calculation. There's nothing in the model that says this calculation has to be done on this node. So sometimes it'll slide to a different node. Because the heads are evolving in parallel, sometimes two heads will learn to do the same task. And so you need both of those heads, working together. And on another training run, it'll just be one head. So within the general approach, there are lots of variants. And in paper 2, we took one of those variations and we analyzed it down to the last degree, and we mapped it to maths, and we said, yay, we're done. We've proved that this one's accurate. But really, that's not what we want to do in the future, because we want to be able to handle those different variations. So what we're moving towards is a mode where we say, if this model is doing arithmetic addition like we think we are, then there must be some node or two nodes which are adding the unit digit from the first, A plus B equals C, the unit digit from A and the unit digit from B, and coming up with the answer. Go off and find that node, because we've got the ablation experiment. We can just apply the ablation experiment to all the nodes until we find that node, right? And so then you end up with your hypothesis is then, if the model's doing addition like I think it is, I must be able to find these 18 different subtasks somewhere in the model, right? And this task must occur before this task, and this task must occur before this task. And so then we won't need to worry if the tasks move around or a task gets split across two nodes. And so we're a reasonable distance towards doing that work. And that seems to be, that's got two benefits. It means that if the model changes the details of how it does calculation, which it was very sensitive to, sometimes it would just change and I couldn't actually understand what I had done that had caused it to change, but it did. So that'll get rid of that. But also that kind of like, here's the addition algorithm. You must be able to find all these components somewhere in the model. We can then just straight apply to the mixed model, right? We say, here's the things that must be occurring for it to be doing addition. Find me those nodes. So that seems like a much more scalable, robust approach. And that's kind of the direction we're heading in, rather than trying to force it to stay with the exact implementation that we inserted into it. Because, and also, like the stricter we are about inserting the model and kind of keeping it at exactly those weightings, the more flexibility we're taking away from the model to evolve a smart way of doing it that we haven't thought of. You know, I guess it's one of our ideas is we don't want to be teaching the model how to do a task. The models are great at learning how to do it themselves, and we don't want to be overly constraining them if we don't have to as they evolve. But we still want compact, accurate, verified, reusable components.
Oh, sorry about that. I had an insect I was trying to.
It's all right. It's all right. I thought you were clapping me.
Well, normally when people clap, they do more than one class. But okay. Yeah. So anyone have a last question for Philip before we go?
I have a quickish question. I was wondering, before you started working on AI safety, had you had any background in transformers, or did you learn everything you know about transformers all in the last, I don't know, I think you said 5 months that you were doing yeah, how long have you been in like this new career direction?
So 6 months ago, August, anyway, last year, I quit my job to study full time. Before that, I was reading articles and blogs and things, but I wasn't doing any coding or any experimentation. I was just getting familiar with the field. So really, it's just in the last 5 or 6 months that I've been reading papers, and I don't achieve it, but I try to read a paper a day, and I'm still only reading the abstract, the diagrams, and the conclusion, unless the paper's really on topic, in which case I go into more depth. And yeah, so in the 5 or 6 months, I've managed to write a couple of papers with help from part research, and possibly on the back of those papers. Like, I'm not saying writing papers is the only way to get into the field. All I can tell you about is my paths. So potentially on the back of those papers, I've got the long-term future fund funding, and the second paper is the basis for my request to OpenAI for a grant for like 3 or 4 people to work on the area. So that's my path.
Do you have any tips for upskilling? Like, what was your strategy for what things to learn and where to learn them from?
So there's a few there's a set of an instructional tutorials called Arena, ARENA, which are very good, and that will get you into Python. It'll get you using Colab, which is you get these Colab notebooks that are a combination of text and code, and they do things, and so you can actually run them and change them and see what they do. There's if you actually want to try to do something novel, there's the 200 questions from Neil Nanda. Somebody, I forget where, is keeping a spreadsheet of who's worked on which questions. So you can look through there and see if anything particularly takes your eye and try and work on it. And the goal, the advantage of that is that if you do manage to discover something, then you can write a paper on it and be reasonably sure that it'll be novel. Apart research. Sorry. There's a Eleuther, ELUEATHA, Eleuther AI. They have a Discord, which is very active, and one of their lead researchers, Nora Belrose, every week she puts out a request for help. So it'll be a request of the community to work on a problem. Says, can people please go at this and see what they can do? So I think you'd have had to make some progress yourself and study before you'd be up for that. But there are organizations that and Apart Research is one of them, that are engaging people who are trying to get into the field and supporting them and providing opportunities to to get a little bit of standing in the community.
Thank you. That's helpful.
Cool. You're welcome.
Cool. Yeah, thank you, Philip. Thank you so much for coming and speaking to us today. Thank you for your time. It's yeah, really, fascinating idea about, reusing, these kind of circuits in language models, and, all the best for your grant or whatever.
Thank you very much.
Yeah, so I'll stick around for a few minutes in case anyone wants to, chat about everything, but otherwise, all the best, and hope everyone enjoys their day.
And thank you, Chris, for keeping this channel going. That was my first entry into the flow of information around the field, and obviously it's just a fire hose. There's just so much information, but ability where you can safely ask questions and just lurk for a while and see what people are talking about is really useful. So well done to you for maintaining these channels.
Thank you. I appreciate it. And if you have any suggestions on how to improve anything, or any suggestions, because you're at a certain stage, you're like, okay, what would have helped me get to this stage? And that, that would be very useful kind of feedback for me.
Cool.
Thanks for organizing these talks, Chris.
Yeah. Cool. All right. Okay, well, yeah, good to see everyone. Okay, bye then.